Hi guys, today we are going to talk about security in microservices architecture. So the question is, why do we even need to talk about security? It is clear that for some applications like banking systems or e-commerce, this is absolutely critical. We have real examples of data breaches. For instance, in 2021, there was a leak of data from 533 million Facebook users from more than 100 countries. Names, phone numbers, birthdays, locations, email addresses. Also, big companies like Microsoft face massive DDoS attacks all the time. These stories show that security is extremely important and nobody denies its critical role. Each of these cases prove that ignoring security can lead to serious financial losses, loss of user trust, and damage to reputation. Okay, continuing our talk about security, we cannot skip OWASP Top 10. It is actually a well-known list of the most critical web application vulnerabilities. In fact, OWASP is an open organization that works to make our software more secure, especially in the web area. So this list works as a standard to identify and fix the most common vulnerabilities. Learning it and applying the right action is very important for reaching the basic level of security in your systems. On the OWASP website, you can find a detailed description of every problem and also practical advice on how to solve it. Actually, it is interesting to see how the list changes with time. For example, the vulnerability injection, which was number one in 2017, moved to third place in 2021. These facts show that the threat landscape is changing and developers are becoming more aware. So, if your company wants to improve security, I would really suggest to start with a deep study and implementation of OWASP Top 10 recommendations. So, now we move to the basic principles of security. The first basic principle is the principle of least privilege. Actually, this means that every entity, a user, a process, or a microservice has only what it really needs to work with. In other words, each service or user gets the minimum access required to do its job, and nothing more. For example, if you have a service that works with payment data, it should only have access to this data. It must not have access to email marketing data if it does not need it. This approach helps to limit attack vectors and reduce risks. Here are some examples. When a service makes an SQL query to a database, it should have only select permissions, but never drop or alter. This prevents accidental or malicious changes that are not part of its real tasks. And in cloud systems like AWS, the role of an EC2 instance working with an S3 bucket should only have access to that one bucket, not to all buckets in the account. So, even if one service is compromised, the attacker will not get full access to the whole infrastructure. In security, we always try to limit access and permissions as much as possible. Actually, a weak level of security can lead to incidents that affect the stability and availability of the whole system. For example, data leaks or DDoS attacks. Let's move to the second basic security principle, defense in depth. Actually, this principle means building a multi-layer defense, where every layer adds its own protection, even if the other layers fail. The main goal is to localize possible breaches and stop a full compromise of the system if one layer is broken. For example, let's look at a common problem, SQL injection. Imagine your web app has a vulnerability in the login endpoint. An attacker sends a malicious payload in the login field, and the server without validation put the string directly into an SQL query. In such a case, the attacker can get access to any user or even the whole user's table because there are no other limits. But what if we use the principle of defense in depth? First layer, web application firewall. It stands at the entry point and blocks most non-malicious requests before they reach the app. Second layer, validation, and prepared statements. Even if the payload passes the firewall, it will not be executed as SQL code because the prepared statement will treat it as normal text. Third layer, database role with limited permissions. Even if the SQL code is somehow executed, the account used by the app can only read certain columns. It cannot delete, update, or change tables. This account may not even have access to very sensitive data like credit cards table. Fourth layer, monitoring system. It records suspicious activity. Any strange requests or access attempts will create alerts, so the security team can react quickly. In fact, in microservices, this principle is even more important. We use network segmentation between microservices. So if an attacker gets into one service, for example, the shipping service, it does not mean he gets access to the order or inventory services. Every microservice should store only the data it really needs and not keep extra data from other services. This way, we reduce the attack surface and localize possible breaches. So, now we move to another very important part of security, secret management. Actually, secrets are any sensitive data like logins and passwords, certificates, API keys, or SSH keys. They are critical for our services and they become a big risk for the company if they are compromised. It is absolutely not allowed to keep such data directly in code, for example, inside YAML files, and even worse, pushed into Git repositories. This is extremely dangerous. That is why we use centralized secret storages, which are secure and regularly audited. For example, solutions like Azure Key Vault, HashiCorp Vault, or the key management service from cloud providers give us many benefits. First, if you need to update credentials for a database or for Apache Kafka, you don't have to change every service that uses them. It is enough to update the secret in the central storage and then just restart the services. They will automatically take the new data. This makes management and rotation much easier. Second, this allows us to apply the principle of least privilege also to secrets. Each microservice should only have access to the secrets it really needs and nothing more. Also, centralized storage makes key rotation much easier. For example, if you find that a key was lost or compromised, maybe posted in a public chat, you can quickly rotate it. In fact, it is also very important to use short-term or session-based credentials with limited lifetime. This reduces the time window for possible attacks if the data leaks. And finally, strong storages like HashiCorp Vault not only keep the keys, but also monitor their use and rotation. Plus, tools like Terraform can automate secret delivery directly to the app during deployment instead of keeping them in files. Okay, continuing our talk about security, we cannot skip the topic of backups. Backups are copies of our data. Actually, they are our insurance against total data loss. In fact, backups also help us recover after deliberate attacks. And it can contain sensitive data, so protecting them is critical. So backups must be created automatically on a regular schedule, for example, daily or at another frequency you choose. This can be a disk snapshot in the cloud or an export from a database. But actually, making backups is not enough. They must be automatically tested so you know they can be restored. In fact, sometimes you try to restore and the backups do not work. Also, all backups, especially those with sensitive data, must be encrypted. This step is not expensive and it is very important. You can use script to mask personally identifiable information like PII. Masked copies let you create test environments with realistic data volume, but without real personal data. So, now let's look at trust models in architecture. And the first one is implicit trust. In this model, there is clearly defined security perimeter. We can imagine it as a private network. Inside this perimeter, we actually fully control the traffic that happens inside. The key idea of implicit trust is that services inside this perimeter completely trust the communication channel. This means that no extra encryption is needed inside this protected area, because we assume no one from outside can reach the internal network. The main advantage of this approach is that it can be faster. In fact, it removes the cost of encryption and decryption for every internal call. For example, when servers send a huge number of HTTP requests to each other, skipping HTTPs inside can really improve performance. But actually, there are also disadvantages. If the external security perimeter is broken, then the whole internal system becomes weaker because the internal services are not protected from each other. The opposite of the implicit model we just discussed is zero trust. Actually, this approach is very different. It says that we have no trust at all. Every service trusts nobody. This means that every interaction between system components must be authenticated, authorized, and encrypted. It doesn't matter if the request comes from outside the security perimeter or if it's just internal communication between two microservices. Every request must pass a full check. In fact, all communication channels are encrypted, often with something like mutual TLS. So each service proves its identity to the other, and both can be sure that they are really talking to the right service. This approach maximizes security. Even if an attacker gets into one service, he cannot move freely across the network, because each next interaction requires authentication and authorization again. This idea fully matches the principle of defend in depth. But of course, there is also a price. Encryption and decryption of every request plus extra checks increase computing costs and can affect performance. Still, despite these costs, zero trust is now the recommended approach in the industry. So, as we said before, the choice of trust model always depends on the specific context of your project, its security needs, and its performance requirements. Now, let's talk about data and its different states. Actually, in security, it is very important to understand that data can exist in three main states, and each of them needs a specific way of protection. The first state is data at rest. This means data stored somewhere, most often in databases, but also in file system, object storages, or any place where data is kept and waiting to be used. The second state is data in transit. This is data moving through the network, for example, between your microservices or between a client and a server. And the third state is data in use. This is data that the application is working with directly in memory while running. A clear example is data used by a client in the browser through JavaScript. So each of these states has its own unique attack vectors. That is why each state needs specific protection methods, and we'll talk about them in more detail on the next slides. So, data at rest means data that is stored in your systems, in databases, on physical disks, in cloud object storages like S3, and also in snapshots or backups. Before you start protection, you need to do information classification. Actually, you should separate personally identifiable information like PII, public data, and critical data to know what level of protection is needed. For example, there is no real reason to encrypt public data because encryption always has some cost. Now here are key principles for protecting data at rest. Passwords must never be stored in plain text. In fact, you should only store their hash with salt. Salt helps protect against brute force and stop the problem where one stolen password opens access to many others. Minimize the collection of PII. For example, if your business logic does not need the full address of the user and only the postal code is enough, store only the code. This lowers risks right away and makes leaks less dangerous. For analytics, teams almost never need PII because they actually work with big volumes and statistics. All data backups must be encrypted, and actually this step is not too expensive to skip. And now let's take a closer look at data in transit. Okay, when data is transferred over HTTP communication, the standard and basic solution is to use HTTPS. I think most of you already know this and configure it. And yes, it is a reliable way to keep confidentiality and integrity of data between client and server. However, special attention should be given to message brokers, such as Kafka or RabbitMQ. People often assume that if everything goes over HTTPS, then brokers are also protected, but this is not always true. In fact, most brokers by default may not provide any authentication when communicating with them, and the communication channels can be unencrypted unless you set it up manually. But both Kafka and RabbitMQ now give you an easy way to configure this. So, another important mechanism for protecting data in transit, especially in microservice architecture, is mutual TLS or mTLS. It is actually quite similar to the TLS we already use in HTTP, but there is one key difference. Not only does the client verify the server, but the server also verifies the client. In normal TLS, when you open a website, your browser only checks the server certificate to make sure it is authentic. But in mutual TLS, both sides exchange certificates and verify each other, building mutual trust. Let's see how it works with two microservices A and B. Okay, service A connects to service B. Service B presents its TLS certificate. Service A verifies service B's certificate. Then service A presents its TLS certificate. Service B verifies service A's certificate. Service B grants access. Service A and Service B now exchange information over an encrypted TLS connection. So this process gives up two-way authentication and encryption, which is extremely important in microservice architecture. Actually, it allows services to fully trust each other's identity, even in unpredictable network environments like cloud infrastructure. That's why mutual TLS has become a de facto standard, not only in microservices. This approach also perfectly fits the zero trust concept. So, the third and probably the most difficult state to protect is data in use. Data in use means data that is actively processed in RAM or in the CPU while the program is running. The main problem is that at this moment the data is not encrypted, and the system must have full clear access to it in order to work correctly. A popular example of this state is data used by the client through JavaScript in the browser. There are attack vectors that focus exactly on this kind of data in memory. For example, an attacker may try to inject a malicious script on the client side. So, how do we protect data while it is in use? The main method is isolation of the execution environment. We use mechanisms like sandboxing, containerization, and micro VMs to limit what the code can do and which resources it can access. Next is memory access control. This includes tools and policies like SE Linux, AppArmor, and memory protection. They make sure that one process cannot read the memory of another process. On the client side, we can also set policies that limit access for third-party scripts. This way, even if malicious code is injected, it cannot send sensitive data outside. So, first, let's clearly separate two key concepts: authentication and authorization. Authentication is a process where we make sure that users are really who they say they are. In fact, it is just identity verification. Authorization is a process where we give the user access to specific resources. So here we check if the user is allowed to use a resource or not. In microservice architecture, there are some specific challenges that make these processes harder. The first one, single sign-on. The user wants to log in only once and then use all microservices without entering credential again. So we need a secure mechanism to work across services. Service-to-service authentication. Actually, not only users need authentication, but also microservices themselves. As we already discussed in the trust models, implicit and zero trust, this part is critical. And now we move to the question of how the single sign-on problem is solved when the user wants to log in only once but use all our microservices. The solution that has become the golden standard is GWT, or JSON Web Token. We talk about it because it perfectly fits into our recommended architecture with the API gateway. By its structure, GWT is not just a key, but a format that contains information inside. It has three parts: header, payload, and signature. The payload or claims can contain user information, like the user ID, role, or required permissions. When a microservice receives such a token, it can immediately see what is inside, without making extra requests to the database or the authentication service. But how do we make sure that this information is trustworthy? This is where the signature comes in, calculated with the HMAC algorithm. This algorithm uses the message like payload and the secret key that our services agreed on. So the signature lets us check two critical things. The first one, that the message was not changed in any way during transmission. And the second one, that the token was generated by a trusted person or service, because only they know the secret key. To check the integrity and authenticity of our GWT, we use the HMAC algorithm, or Keyed Hash Message Authentication Code. Even though we talk about GWT here, the concept of HMAC is useful in any context where we need to make sure that the information was not changed and was created by a trusted source. How does it work? Our two services, for example, service A and service B, first agree on a shared secret key. When service A wants to send a message, it takes the message itself, for example, the payload of our GWT, and the secret key. And with a hash algorithm, it generates a signature. Then service A sends the message and this signature to service B. Notice the message the payload itself is sent in plain, not encrypted form. Service B, after receiving the message and also having the secret key, can calculate the same hash. After that, it checks if the hash sent by service A is the same hash it calculates. If the hash is matched, this proves that the data was not changed and the token is authentic. Okay, the question of how long our GWT token should live is open for discussion, but there is a very common approach that gives a balance between security and convenience. It is the use of two tokens, access token and refresh token. The access token is our GWT itself. It is used all the time to access microservices. Its lifetime is usually very short, maybe only for one session or even for a single request. It is done to limit the window of possible compromise. If this token is stolen, the attacker can use it only for a short period of time. The refresh token has a much longer lifetime. Its job is to get a new access token when the old one expires. Why is this great in the context of microservices? Better security. The main advantage is the ability to limit the lifetime of the access token much more strictly. If the access token is lost, it quickly becomes useless. Convenience. The user does not need to enter credential again and again, which support the idea of single sign-on. The user logs in once, and then the system automatically refreshes the access token with the refresh token, without interrupting the work. So let's look at the recommended authentication architecture in microservices with API gateway and GWT, following the single sign-on problem. The process works like this. The client makes a request, it goes to our API gateway. The API gateway is a single entry point and it calls the authorization service, which has its own database to check the credentials. After successful authentication, the service sends back a GWT to the API gateway, which then forwards it to different services. A critical architectural point is that the authentication service is not placed between services. Only the API gateway communicates with it. This makes monitoring and access control easier, and it also protects the authentication service since it is not open to the whole internal network. The GVT is used to carry the user context between services. This is the biggest advantage of the token because it contains all necessary information, from the user ID to role and permissions. Microservices can then validate the same GVT locally. Local validation lets microservices immediately checks its authenticity, reducing the number of extra calls to the authentication service or the database, since all the needed data is already inside the token. In this way, we keep the high performance while also keeping a high level of security. Okay, today we have gone a long way and looked at the key things without which microservice architecture simply cannot survive. We have things that security is not an option, it is a necessity. Data leaks, DDoS, and attacks on big companies show us that the risks are real and the consequences are serious. The first level is OWASP Top 10. This is the base where you should start. Then we talk about the principle of least privilege and defense in depth. These are fundamental ideas: limit access, add layers of defense, localize risks. A critical topic is secrets, not in code, not in YAML, but in special secret storages, and only with minimal access, plus rotation and short TTLs. We also looked at backups. It is not enough to have them. You must test that they really restore, and always keep them encrypted. Then we move to trust models. On one side, implicit trust, on the other, zero trust, which requires authentication and encryption at every step. We protect data in three states: at rest, in transit, and in use. Each state has its own attack vectors and its own protection methods. And finally, we covered authentication and authorization. Single sign-on, GVT as the golden standard, short-lived access tokens plus refresh tokens. So the conclusion is simple. Security in microservices is not one feature, but a whole ecosystem of solutions and principles that must be applied together. And let's wrap this up with a short quiz. Okay, this was a last lecture of this course. Thank you all for being with me. Hope see you soon. Bye bye.